Please subscribe to support the channel. How fast can we really travel in space right now? It's a question that blends wonder with reality. Not about science fiction starships or warp drives, but about the limits of human technology today. In just a few decades, we've gone from barely escaping Earth's atmosphere to sending probes racing across the solar system at unimaginable speeds. Yet even our fastest spacecraft are still crawling compared to the cosmic scale. This isn't just about numbers. It's about how far human ingenuity has taken us, how we measure motion in the vastness of space, and what those speeds truly mean for our journey into the universe. When we talk about speed on Earth, it's a fairly simple idea: how fast something moves from one point to another relative to the ground beneath it. But in space, that concept becomes far more complex, because in the vast emptiness beyond our planet, there is no fixed ground, no universal frame of reference. Every motion is relative to something else: a planet, the sun, or the stars themselves. So before we can truly answer how fast we can travel in space, we first need to understand what fast even means up there. In space travel, velocity is always relative. When engineers or scientists describe the speed of the spacecraft, they must choose a point of reference, and that choice completely changes the number. A satellite orbiting Earth, for example, might be moving at around 28,000 kilometers per hour relative to the ground below it. But from the perspective of the sun, both the satellite and the Earth are already moving at about 107,000 kilometers per hour as our planet races through its orbit. In other words, that same satellite has two very different speeds depending on what you're comparing it to. This relativity is at the heart of space navigation. Because the universe doesn't have a universal zero point of rest, every motion is measured against something else. For instance, when NASA announces that a spacecraft is moving at a certain velocity, it often clarifies relative to what? The Earth, the Sun, or sometimes the heliocentric frame, meaning the spacecraft's motion around the Sun. For interplanetary missions, speeds are typically measured relative to the Sun because it provides the most stable frame of reference for objects traveling across a solar system. The difficulty of defining fast in space becomes even clearer when we consider how objects move together. Earth, for instance, rotates around its axis at about 1,670 kilometers per hour at the equator. On top of that, it orbits the Sun at roughly 107,000 kilometers per hour. The Sun itself, in turn, is moving through the Milky Way at an estimated 828,000 kilometers per hour relative to the galactic center. Add those motions together, and you realize that every one of us, sitting still in a chair right now, is already hurtling through the cosmos at mind-bending speeds. But because everything around us moves with us, we feel nothing. That's the strange beauty of motion in space. Speed is everywhere, yet it's invisible to us. For spacecraft, this relativity means that fast isn't always about sheer numbers, it's about context. A rocket that escapes Earth's gravity at 11 kilometers per second is moving extremely fast relative to Earth. But relative to the Sun, it might only be moving slightly faster or slower than our planet itself. When that same spacecraft travels toward Mars or beyond, its velocity constantly changes depending on which gravitational body dominates its motion. Sometimes, spacecraft even appear to slow down or speed up when viewed from Earth, simply because of changing perspectives in orbital geometry, not because their engines are firing or coasting. This is why mission planners and physicists often use the concept of heliocentric velocity, or barycentric velocity, speeds measured relative to the center of mass of the solar system. It gives a more consistent sense of motion when describing objects that move across planetary orbits. However, even that has its limits, because everything in the universe, from galaxies to clusters of galaxies, is in constant motion. There's simply no universal speedometer to measure against the cosmos as a whole. Another layer of complexity arises from the fact that motion in space isn't resisted by friction like it is on Earth. Once a spacecraft is accelerated to a certain velocity, it can maintain that speed indefinitely, barring gravitational influences. There's no atmosphere to slow it down, no air resistance to fight against. This means that fast in space isn't just about how quickly something can go, it's also about how efficiently it can keep going. A spacecraft that slowly accelerates over months using a low-thrust engine can eventually achieve much higher speeds than one that burns all its fuel in a few minutes during launch. Moreover, In the language of physics, what often matters more than speed itself is velocity, a vector quantity that includes both magnitude, how fast something is moving, and direction, where it's going. In orbital mechanics, changing direction can be just as energy-intensive as changing speed. For example, turning a spacecraft's trajectory slightly in space can require vast amounts of fuel, even if its overall speed remains nearly the same. That's why space missions are planned with such precise timing and geometry. Every bit of motion must be calculated relative to the moving targets and gravitational forces in the solar system.
In this context, fast becomes a multidimensional idea. It can refer to orbital speed, escape velocity, or transfer velocity, each one representing a different kind of motion relative to celestial bodies. It can mean how quickly an object moves around a planet, how fast it must travel to break free of that planet's gravitational pull, or how rapidly it's moving through interplanetary space compared to the Sun. Every one of these fasts is true in its own frame, and all are essential to understanding how humans travel through the cosmos. So when we ask, how fast can we travel in space, the real answer depends entirely on where you're standing, or more accurately, what you're standing relative to. Our spacecraft might seem to crawl when compared to the vast scale of interstellar distances, but relative to human experience, they're already moving at extraordinary speeds. It's this relativity, this fluid, shifting measure of motion, that makes the question so fascinating and so difficult to answer in absolute terms. In the end, fast in space is not a single number, but a story told through relationships between planets, stars, and the machines we send to explore them. It's about perspective, precision, and the incredible challenge of navigating a universe where nothing ever truly stands still. Even before a rocket ever leaves the ground, we're already passengers on one of the fastest moving objects in existence, our own planet. While standing still may feel like absolute stillness, the truth is that Earth is constantly in motion, spinning, orbiting, and racing through space at astonishing speeds. Understanding these natural motions gives us a powerful sense of scale, a reminder that speed, in the cosmic sense, is both relative and unimaginably vast. Let's start with Earth's rotation. Our planet spins once every 24 hours, completing a full turn on its axis. That rotation is what gives us day and night, but it also means that every single point on Earth's surface is moving through space. The speed of this rotation depends on where you are. At the equator, where the circumference of Earth is largest, you're traveling at about 1,670 kilometers per hour, or roughly 465 meters per second, as the planet turns beneath the stars. You don't feel it because everything around you, the air, the oceans, the land, is moving at the same rate. But if the Earth were to suddenly stop spinning, everything not anchored to bedrock would be flung eastward at over 1,000 kilometers an hour. That's how powerful our planet's rotation really is. As you move toward the poles, the speed of rotation decreases, because the circumference of Earth's path gets smaller. At the North or South Pole, you're essentially spinning in place, completing one rotation every 24 hours, but covering no horizontal distance. It's a strange thought. Depending on where you stand, you're either hurtling through space at over 1,000 kilometers an hour, or you're simply pirouetting on the axis of the world. But Earth's rotation is just the beginning. Our planet is also orbiting the Sun at a breathtaking velocity of about 107,000 kilometers per hour, or roughly 30 kilometers per second. This orbital motion means that every second we move about 8 kilometers along our curved path around the Sun. In just 1 year, Earth completes a 940 million kilometer journey through space. And yet we perceive none of it. Day after day, the ground feels solid beneath our feet, while in truth, we're racing through the solar system at over 100,000 kilometers every single hour. And that's still not the full picture. The Sun itself is in motion, carrying Earth and the rest of the solar system along as it orbits the center of the Milky Way galaxy. Our star travels at around 828,000 kilometers per hour, or roughly 230 kilometers per second, relative to the galactic core. When you combine that with Earth's own orbital and rotational motion, it means that right now, as you're listening or reading this, you're moving through the universe at well over 1 million kilometers per hour. And yet, because all of these motions are constant and shared by everything around us, we feel completely still. To make this even more astonishing, consider that the Milky Way itself isn't stationary either. The entire galaxy is drifting through space at roughly 2.1 million kilometers per hour, relative to the cosmic microwave background, the faint radiation left over from the Big Bang. This means that on the largest scales imaginable, even our galaxy is a traveler, sweeping through the vastness of intergalactic space. So when we talk about how fast we can travel in space, we must remember that we're already moving at cosmic speeds just by existing. Our planet, our star, and our galaxy are all part of a grand celestial ballet, a choreography of motion that defines the very fabric of the cosmos. Every spacecraft we launch begins its journey not from rest, but from a world already hurtling through space at mind-bending velocities. This perspective is humbling because it reframes our sense of motion. Even our fastest rockets are merely tiny adjustments added on top of the colossal velocities that nature already provides. When a spacecraft escapes Earth's gravity, it's not starting from zero. It's joining the endless dance of motion already in progress, a dance that began billions of years ago when the solar system first formed. It's also worth noting how this motion affects the way we measure speeds in space. Because Earth is constantly moving, a spacecraft's velocity relative to our planet can change dramatically depending on whether it's traveling in the same direction as Earth's orbit or against it. Launching a rocket eastward, for instance, takes advantage of the planet's rotation, giving it an extra boost of up to 1,670 kilometers per hour at the equator. That's why most major launch sites, like NASA's Kennedy Space Center, are located near the equator and launch toward the east. We're literally using the planet's spin to help push our spacecraft into orbit. The same principle applies on a larger scale, with Earth's orbital velocity. When sending spacecraft to other planets, mission planners often time launches so that the direction of travel aligns with Earth's motion around the Sun, giving the spacecraft a head start. It's a subtle but critical detail, one that shows how even our planet's own speed becomes part of the equation in reaching beyond it.
From the smallest rotation to the grandest galactic drift, motion defines our existence. We are never truly still, not for a single moment. The idea of being stationary is an illusion born of perspective. We live aboard a spinning, orbiting, racing world, one that has been soaring through the cosmos for billions of years. And yet, for all this natural motion, human technology has managed to push even further. When we start talking about spacecraft, machines that can change their motion relative to these cosmic speeds, we enter a new realm of achievement. These creations, built by human hands, can not only ride along with the planet's natural movement, but accelerate far beyond it. Next, we'll explore how humanity first began to build such machines, and how, in just a few generations, we've learned to craft vehicles capable of escaping the pull of our fast-moving world and venturing into the infinite expanse beyond it. As astonishing as Earth's natural motion is, the real story of how fast we can travel begins when humanity decided not just to ride along with the planet's cosmic journey, but to take control of its own motion. For most of history, humans were bound to the surface of the Earth, limited to walking, sailing, and eventually flying through the air. But none of those feats came close to the raw, unrestrained speeds achieved once we began building spacecraft. These machines represent a monumental leap in our ability to harness energy, defy gravity, and move through space in ways nature never intended for us. Spacecraft are humanity's speed champions, by far the fastest objects ever created by human hands. On Earth, even the most advanced airplanes and vehicles are confined by air resistance, friction, and gravity. The fastest jet ever built, the legendary Lockheed SR-71 Blackbird, reached speeds around 3,500 kilometers per hour, Mach 3.3, an incredible achievement for atmospheric flight. Yet the moment we step beyond the atmosphere, the rules change completely. Without air resistance and with the freedom to coast through the vacuum of space, our spacecraft can achieve velocities that make even the fastest jets seem frozen in comparison. Once a rocket escapes Earth's atmosphere, it's no longer held back by drag or slowed down by the air. The only significant forces left are gravity and the momentum imparted by its engines. In this frictionless environment, speed becomes something far more enduring. A spacecraft doesn't need to maintain thrust to keep moving. Once it accelerates to a certain velocity, it will continue coasting at that speed indefinitely, unless acted on by another force, such as the gravity of a planet or the subtle pressure of sunlight. This ability to maintain motion transforms how we think about travel. On Earth, a car that stops accelerating quickly slows to a halt. In orbit, a spacecraft that shuts off its engines remains in motion forever. That's why every bit of velocity gained during launch is precious. It determines how far the craft can go, how fast it can travel between worlds, and whether it can escape Earth's gravitational well entirely. From the very first rockets, humanity learned that space travel isn't just about reaching the sky, it's about achieving velocity. The challenge of spaceflight is not simply climbing upward, it's going fast enough sideways to stay in orbit or fast enough outward to break free of gravity. This realization redefined what speed means to us. It became not just a measure of movement, but a gateway to exploration itself. Once engineers understood the fundamentals of orbital mechanics, they realized that the higher a spacecraft's velocity, the greater its freedom. A satellite traveling at around 28,000 kilometers per hour can maintain a stable low Earth orbit. Anything slower would fall back toward the surface. To leave Earth altogether, to escape its gravitational well, a spacecraft must reach an even more incredible speed, one that no airplane or terrestrial vehicle could ever hope to achieve. And that's exactly what our rockets were designed to do. These towering machines, part fuel tank, part precision instrument, convert immense amounts of stored chemical energy into motion, hurling spacecraft into the heavens at speeds that defy intuition. When a rocket launches, it's not simply climbing, it's accelerating sideways fast enough for its falling path to match the curve of Earth's surface, creating a continuous state of freefall known as orbit. What's even more fascinating is that each generation of spacecraft has pushed the limits of speed further and further. The early space missions of the 20th century were modest by today's standards, but they laid the groundwork for everything that came after. From the primitive rockets that barely brushed the edge of space to the mighty Saturn V that carried astronauts to the moon, each step represented a triumph of engineering and a leap in how fast humans could travel.
These spacecraft are not just machines, they're symbols of possibility. They embody our curiosity, our courage, and our relentless drive to test what's possible. When we measure their speeds, we're not just counting numbers, we're measuring the boundaries of human capability itself. Because in the end, every record we break, every kilometer per second we achieve, brings us a little closer to bridging the unfathomable distances that separate us from the stars. And as we'll soon see, the journey from those early rockets to today's fastest probes tells a story of both scientific genius and human daring. A story that begins in the 1950s, with our first tentative steps into the void. When humanity first broke free from Earth's surface, it wasn't just a leap in altitude, it was a leap in velocity. The early days of spaceflight were a series of bold experiments in speed, each mission pushing further and faster than anything that had ever flown before. In a few short years, we went from propeller-driven aircraft barely reaching the stratosphere to rockets capable of piercing the boundary of space and achieving orbital velocity. It was the dawn of a new era, one where speed was no longer measured in kilometers per hour, but in kilometers per second. To appreciate just how far we leapt, it helps to remember where we started. Before rockets, the fastest machines on Earth were jet-powered aircraft. During the 1950s and 1960s, aircraft like the Bell X-1 and the X-15 were at the cutting edge of aviation technology. The Bell X-1, famously piloted by Chuck Yeager in 1947, became the first aircraft to break the sound barrier, reaching speeds of about 1,200 kilometers per hour, or Mach 1.0. A decade later, the X-15 rocket plane shattered that record, achieving an incredible 7,200 kilometers per hour, or Mach 6.7, and briefly touching the edge of space. Those numbers were astounding, but they still fell far short of the speeds required to orbit Earth. To achieve orbit, a spacecraft must travel at about 28,000 kilometers per hour, or 7.8 kilometers per second. That's nearly 4 times faster than the X-15, and at the time, it seemed almost impossible. Yet, by the late 1950s, humanity was on the verge of doing exactly that. The Soviet Union's Sputnik 1, launched on October 4, 1957, marked the first true leap into orbital speed. The small spherical satellite circled Earth at roughly 28,800 kilometers per hour, or 8 kilometers per second. For the first time, a human-made object was moving fast enough to continuously fall around the Earth instead of back toward it. Just a month later, the Soviets launched Laika, the dog, aboard Sputnik 2, demonstrating that living beings could survive, at least for a time, at such blistering velocities. The United States soon followed. In 1961, Alan Shepard became the first American in space aboard Freedom 7, part of NASA's Mercury program. His flight was suborbital, lasting only about 15 minutes, and reached a maximum speed of 8,260 kilometers per hour. Fast enough to leave the atmosphere, but not fast enough to stay in orbit. Later that same year, Soviet cosmonaut Yuri Gagarin made history as the first human to orbit Earth aboard Vostok 1. His spacecraft reached speeds of about 27,400 kilometers per hour, or 7.6 kilometers per second. Humanity had officially entered the age of orbital travel. The Mercury program quickly advanced from brief suborbital hops to full orbital missions. Friendship 7, piloted by John Glenn in 1962, orbited Earth 3 times at speeds approaching 28,000 kilometers per hour, matching the velocity required to maintain orbit. Glenn's journey was a defining moment. Not only was he moving 8 times faster than a bullet, but he was also part of a world-changing realization that humans could live, work, and return safely from the realm of orbital motion. Building on Mercury's success, NASA's Gemini program, 1965 through 1966, expanded the frontier of speed and endurance. Gemini spacecraft routinely orbited Earth at around 28,000 kilometers per hour, the same orbital velocity, but stayed aloft for days instead of hours. These missions allowed astronauts to practice critical maneuvers like docking, reentry control, and spacewalking, skills that would later be essential for reaching the moon. Then came the Apollo missions that didn't just orbit Earth, they left it entirely. The difference in speed between reaching orbit and escaping Earth's gravity is immense. To break free of Earth's pull, a spacecraft must reach what's known as escape velocity, about 40,000 kilometers per hour, or 11.2 kilometers per second. When the mighty Saturn V rocket launched the Apollo spacecraft toward the moon, it did exactly that. During the Apollo 10 mission in May 1969, a full dress rehearsal for the moon landing, the spacecraft reached a top speed of 39,897 kilometers per hour, or 11.11 kilometers per second. That record remains one of the fastest speeds ever achieved by human beings. It's hard to comprehend what that velocity means. At that speed, you could travel from New York to London in just 18 seconds. The Apollo astronauts experienced firsthand what it felt like to ride the very edge of human capability. To put all of this into perspective, the fastest passenger jets today, like the Boeing 747 or the Concorde during its time, cruise between 900 and 2,200 kilometers per hour. The Apollo astronauts were moving nearly 20 times faster than the Concorde and about 45 times faster than the speed of sound. That's not just a leap forward, it's an entirely different category of motion.
What's even more remarkable is how each of these early missions paved the way for greater and greater speeds. The Mercury missions proved humans could survive in space. Gemini demonstrated that we could maneuver and operate there. Apollo showed that we could leave our planet altogether. Each step built on the lessons of the one before it, creating a foundation for everything that would follow, from interplanetary probes to deep space exploration. The early space era wasn't just a technological triumph, it was a redefinition of what it meant to move. For the first time in history, we weren't just traveling on a planet, we were traveling between worlds. The numbers may sound clinical, thousands of kilometers per hour, meters per second, but behind those numbers was something profoundly human. The desire to go faster, farther, and deeper into the unknown.
And as we'll see next, achieving those speeds wasn't just a matter of power. It was a matter of physics. The next great leap in our journey came from understanding a single crucial idea: that to escape Earth completely, you must reach a very specific threshold, one known as escape velocity. Every journey into space, no matter how ambitious or distant, must begin by overcoming one fundamental barrier: Earth's gravity. This invisible force binds everything, oceans, air, satellites, and even the moon itself, to our planet. Escaping its grip requires not just height, but speed. And that's where one of the most important concepts in space travel comes into play: escape velocity. Escape velocity is the minimum speed an object must reach to break free of a celestial body's gravitational pull without needing any further propulsion. In simpler terms, it's how fast you have to go to leave Earth and never fall back down. For our planet, that number is staggering, about 11.2 kilometers per second, or roughly 40,300 kilometers per hour. To understand why such an immense speed is necessary, imagine throwing a ball straight up into the air. It rises for a moment, slows as gravity pulls it back, and eventually falls to the ground. The harder you throw it, the higher it climbs before gravity wins. If you could somehow throw it fast enough that Earth's gravity could never pull it back, that speed would be the escape velocity. In essence, it's the point at which your kinetic energy equals the gravitational binding energy of the planet. The concept isn't just theoretical, it defines the very physics of space travel. Rockets don't typically reach escape velocity in one instant, like a thrown ball. Instead, they accelerate gradually, countering gravity over time, rather than relying on one explosive push. The idea of escape velocity simply defines the total energy required to leave, whether that energy comes all at once or over several minutes of powered flight. Once a spacecraft reaches escape velocity, a remarkable thing happens. It's no longer bound to Earth. Its trajectory changes from a closed orbit, where it would circle the planet indefinitely, to an open one, a hyperbolic or parabolic path, meaning it's free to drift away into the vastness of space. From that moment on, the spacecraft is in the domain of the sun's gravity rather than Earth's, joining the endless cosmic dance of celestial motion. What makes this so profound is that it defines a universal truth of travel in space. Speed equals freedom. The faster you go, the weaker the gravitational chains become. Every world, every moon, every star has its own escape velocity, its own threshold of liberation. And crossing that line is the difference between being trapped and being free to explore the cosmos. The challenge of achieving escape velocity is also what drives so much of rocket design. Reaching it demands enormous amounts of energy, and energy in rocketry means fuel. That's why rockets are so massive. The majority of their mass is propellant burned in a matter of minutes just to give a relatively tiny payload enough speed to reach orbit or beyond. Engineers must balance fuel efficiency, thrust, and structural limits, all to deliver just enough velocity to overcome gravity's relentless hold. In a sense, every rocket launch is a delicate tug-of-war between human ambition and planetary gravity. Gravity never weakens, but with each generation of rockets, our engines have grown more powerful, our trajectories more precise, and our understanding of orbital mechanics more refined. Once we mastered how to reach escape velocity, the solar system opened up to us. No longer confined to Earth's orbit, we could send spacecraft to the moon, to Mars, and to the outer planets. This was the true beginning of interplanetary exploration, a triumph that turned a simple number, 11.2 kilometers per second, into a symbol of human liberation. And perhaps the most famous demonstration of that liberation came during the Apollo era. When astronauts aboard the Saturn V rocketed toward the moon, they not only achieved escape velocity, but did so carrying the hopes of an entire species. Their journey proved that we could break the bonds of our planet, that we were capable of venturing beyond.
Next, we'll explore those missions in greater detail, the Apollo voyages themselves, and discover how even decades later, the speeds reached by those brave crews remain among the fastest ever achieved by human beings. The Apollo missions were not just milestones in human exploration, they were triumphs of speed, precision, and courage. For the first time in history, human beings were not merely orbiting their home planet, they were setting course for another world. And to do so, they had to travel at velocities that remain, even to this day, among the fastest speeds ever reached by humanity. The numbers alone are awe-inspiring, but what they represent, the mastery of motion on a cosmic scale, is even more profound. When the Saturn V rocket thundered to life on the launch pad, its 3 massive stages worked together to deliver the Apollo spacecraft into orbit. The first stage lifted the rocket off the ground, burning over 2.5 million kilograms of fuel in just a couple of minutes. The second stage carried it higher, pushing it beyond the densest layers of the atmosphere. By the time the third stage, the SIVB, took over, the astronauts were already traveling at roughly 28,000 kilometers per hour, the speed needed to remain in low-Earth orbit. But that was only the beginning. To leave Earth behind and begin the journey to the Moon, the spacecraft had to fire its third stage engine one final time in what's known as the Trans-lunar injection, TLI. This maneuver boosted the spacecraft velocity to about 39,000 kilometers per hour, or 10.8 kilometers per second, fast enough to escape Earth's gravity and enter a long, curved trajectory toward the Moon. That acceleration transformed the astronauts from Earth-orbiting travelers into deep space voyagers. At that speed, the Apollo spacecraft covered over 1,000 kilometers every minute. In less than 4 hours, it had traveled farther from Earth than any human in history had before. The astronauts could look back and watch their planet shrink rapidly into a bright blue sphere, glowing in the blackness of space. The feeling must have been indescribable. To witness the Earth recede at tens of thousands of kilometers per hour, knowing that every passing second carried them farther from home than anyone had ever dared to go. The Apollo mission's top speeds weren't just impressive, they were absolutely necessary. The physics of celestial mechanics demanded it. If the spacecraft had traveled slower, it wouldn't have reached the Moon. It would have fallen back into Earth's gravitational grip. Too fast, and it might have overshot the Moon entirely. NASA's engineers had to calculate the velocity to an extraordinary degree of precision, a delicate balance of energy and trajectory that left virtually no room for error. During Apollo 10, the final test flight before the historic Moon landing, the returning spacecraft set a human speed record that still stands today. As it re-entered Earth's atmosphere, it reached the peak velocity of 39,897 kilometers per hour, or 11.08 kilometers per second. That's nearly 11 times faster than a rifle bullet and 50 times faster than the sound barrier. To put it another way, at that speed, you could circle the entire Earth in about 37 minutes. No human has ever traveled faster since. When Apollo 11 launched in July 1969, carrying Neil Armstrong, Buzz Aldrin, and Michael Collins, it followed the same trajectory. After the TLI burn, their spacecraft coasted toward the Moon at roughly 39,000 kilometers per hour relative to Earth. The trip took about 3 days, but their speed wasn't constant. As they moved away from Earth, gravity gradually slowed them down. By the time they reached lunar orbit, their speed had dropped to around 3,600 kilometers per hour, slow enough to be captured by the Moon's gravity. Then, on the way back home, gravity reversed its role, pulling them toward Earth and accelerating them once again to nearly 40,000 kilometers per hour before re-entry.
Re-entering the atmosphere at that speed posed one of the greatest engineering challenges in human history. The friction of the air compressed by the spacecraft's blunt heat shield created temperatures of over 2,700 degrees Celsius, hot enough to melt steel several times over. To survive, the Apollo capsules were coated with a blade of material that vaporized and carried the heat away, forming a fiery plasma around the spacecraft as it streaked through the sky. For a few terrifying minutes, the astronauts were completely cut off from radio contact as the plasma blocked communications. Then, at just the right angle and speed, the capsule slowed enough to deploy its parachutes and splash down safely in the ocean. The sheer magnitude of those speeds is difficult to grasp even today. When we talk about 39,000 kilometers per hour, it's easy to lose sight of what that means in human terms. Imagine driving down a highway at 100 kilometers per hour, fast enough to feel the wind rush by and the world blur slightly at the edges. Now multiply that feeling nearly 400 times and remove the comforting hum of the earth beneath your wheels. That was the reality for the Apollo astronauts, hurtling through the emptiness of space at a velocity so great that Earth itself seemed to shrink behind them. It's worth remembering that every Apollo mission required not just brute speed, but also delicate control. Each change in velocity, whether to enter lunar orbit, land on the surface, or return home, had to be executed with flawless precision. A few seconds too long on a rocket burn or a fraction of a degree off course could mean missing the moon entirely or skipping off Earth's atmosphere like a stone on water. Every movement was calculated, rehearsed, and timed down to the heartbeat. The Apollo era marked the pinnacle of human speed. Even with today's technology, no crewed spacecraft has surpassed those velocities. The International Space Station, for instance, orbits Earth at about 28,000 kilometers per hour. Fast, yes, but still far slower than the lunar return speeds of Apollo. That fact alone underscores how monumental those missions were. In an age of slide rules and analog computers, engineers managed to send humans farther and faster than anyone has since. These incredible velocities were not just numbers on a gauge, they were the tangible evidence of human determination to transcend limits. Each Apollo flight was a declaration that our species could overcome the forces that held us to one world and reach another. And though we haven't yet sent people farther than the moon, the speeds achieved by those missions still serve as a benchmark, a reminder of what's possible when courage, ingenuity, and physics align perfectly. But while Apollo represents the fastest humans have ever traveled, the story of space speed doesn't end there. Beyond the limits of human endurance, we've built machines, robotic explorers, that have gone even faster. Freed from the constraints of human safety, these spacecraft have shattered speed records and ventured into regions of space where no person could survive. When humans first left Earth orbit during the Apollo missions, they achieved breathtaking speeds, tens of thousands of kilometers per hour, but even those remarkable numbers pale in comparison to what came next. Once we removed the most fragile part of the equation, ourselves, we unlocked an entirely new frontier of velocity. Robotic spacecraft, free from the limitations of human biology, have become the true speed champions of our species. They've raced past planets, skimmed the edge of the sun, and even left a solar system behind, all at speeds that would be fatal for any living passenger. The advantage of robotic spacecraft is simple but profound. They don't need to come back. They don't need food, water, or breathable air. They don't have to endure crushing G-forces or survive the blistering heat of atmospheric reentry. Without the burden of human safety, these machines can take risks and accelerations that would be unthinkable for crewed missions. This freedom has allowed engineers to design probes that push the very limits of physics, reaching velocities that make even Apollo's record-breaking flights seem modest.
The story of uncrewed speed began almost alongside the dawn of space exploration itself. Just months after Yuri Gagarin became the first human in orbit, the Soviet Union's Venera probes began their race toward Venus. These early robotic missions reached speeds of around 40,000 kilometers per hour, fast enough to escape Earth's gravity and set course for another planet. Not long after, NASA's Mariner program achieved similar velocities, sending spacecraft to study Venus, Mars, and Mercury during the 1960s and 1970s. For the first time, humanity wasn't just visiting space, we were beginning to travel through it. One of the earliest record holders among robotic missions was Helios 2, launched in 1976. This German-American probe was designed to study the Sun, and its unique trajectory brought it closer to our star than any spacecraft before it. As it swung around the sun, gravity pulled it to an astonishing 252,800 kilometers per hour, or 70.2 kilometers per second, more than 6 times faster than Apollo's top speed. At that pace, Helios 2 could travel from New York to Los Angeles in just 36 seconds. For decades, it remained the fastest human-made object in history. Such speeds are not achieved simply by raw rocket power. They're the result of careful use of gravity, what scientists call gravity assists or slingshot maneuvers. By flying close to planets, spacecraft can borrow a little bit of their orbital momentum, gaining tremendous speed without expending additional fuel. This technique became a cornerstone of interplanetary travel, and robotic probes were the perfect test beds for mastering it. In 1977, NASA launched the Voyager 1 and Voyager 2 spacecraft, twin robotic explorers destined to study the outer planets and then continue into interstellar space. Thanks to multiple gravity assists from Jupiter and Saturn, Voyager 1 reached speeds of about 61,000 kilometers per hour relative to the Sun. It's still traveling outward today, over 22 billion kilometers from Earth, and remains the most distant human-made object in existence. Though it slowed slightly due to the Sun's gravitational influence, it's still racing through the void at nearly 17 kilometers per second, an incredible testament to human engineering from nearly half a century ago. Following Voyager's success, other missions pushed the limits even further. The Galileo probe to Jupiter, the Cassini-Huygens mission to Saturn, and New Horizons, which famously flew past Pluto in 2015, all relied on complex trajectories that combined rocket propulsion with planetary flybys to achieve unprecedented speeds. New Horizons in particular broke records of its own. After launch in 2006, it left Earth at 58,000 kilometers per hour, or 16 kilometers per second, the fastest launch speed ever achieved by a spacecraft departing our planet. With a boost from Jupiter's gravity, it accelerated to about 83,000 kilometers per hour, racing toward Pluto across nearly 5 billion kilometers of space in just 9 years. These robotic missions revealed a crucial truth. In the quest for speed, human limits are not technological, they're biological. Our spacecraft can easily go faster than our bodies could ever endure. The G-forces required to accelerate a human to even a fraction of the speeds reached by robotic probes would be lethal. The heat, radiation, and energy involved in close solar passes would destroy any life support system. Machines, on the other hand, can be built to survive where we cannot, hardened against radiation, heat, and the silence of interstellar space. As robotic technology improved, so did our ambition of our missions. Each new probe became both a scientific tool and a test of our ability to control motion at cosmic scale. Spacecraft like Ulysses, Messenger, and BepiColombo explored the inner solar system, each using multiple planetary flybys to reach unprecedented speeds while studying the Sun, Mercury, and other celestial bodies. Every mission refined our mastery of orbital mechanics, a discipline where speed, gravity, and timing converge in a dance of mathematical precision. Perhaps most impressively, these robotic missions demonstrated that the universe itself can be a kind of engine. By falling toward massive bodies and skimming past them, spacecraft can harness gravity to gain speed without fuel, turning planets and stars into stepping stones for acceleration. This technique not only allows us to reach higher velocities, but also saves enormous amounts of propellant, making long-range exploration possible. This understanding paved the way for the next great leap, a spacecraft designed not just to pass by the Sun, but to dive into its inferno. NASA's Parker Solar Probe, launched in 2018, would use multiple Venus flybys to gradually tighten its orbit around the Sun, trading altitude for speed in one of the most extreme missions ever attempted. With each close pass, it would accelerate to previously unimaginable velocities, eventually smashing through every existing speed record.
The robotic age of exploration taught us that speed is more than a number. It's a tool, a means of unlocking new frontiers. Every probe sent farther or faster than the last expands not just our reach, but our understanding of what's possible. Freed from the delicate constraints of human life, our machines have become our messengers, carrying humanity's ambition to the very edges of the solar system and beyond. And with Parker's solar probe, that ambition reached its most thrilling expression yet. By venturing closer to the Sun than any spacecraft before it, Parker didn't just set a new record, it redefined the meaning of fast itself. The story of speed in space reaches its breathtaking climax with one extraordinary machine, NASA's Parker Solar Probe. If every spacecraft before it represented a step toward understanding how fast we could go, Parker is the leap. It's not just the fastest human-made object ever built, it's the first spacecraft designed to touch the Sun, diving into its fiery atmosphere where no other probe has dared to venture. In doing so, it has shattered every speed record in history, reaching velocities so extreme that the numbers themselves almost defy imagination. Launched on August 12, 2018, atop a Delta IV Heavy rocket, the Parker Solar Probe's mission was as bold as it was dangerous: to travel closer to the Sun than any spacecraft in history, collecting data about its outer atmosphere, the corona, and unlocking secrets about solar winds and magnetic fields that shape the entire solar system. To achieve this, Parker had to do something paradoxical. It had to slow down relative to the Sun. Because Earth orbits our star at about 107,000 kilometers per hour, and to fall inward toward the Sun, Parker had to shed some of that orbital momentum. Yet in doing so, as it fell deeper into the Sun's gravity well, it began to accelerate to mind-bending speeds. Unlike a car that slows down when it goes downhill, Parker speeds up as it falls toward the Sun, pulled by the immense gravity of our nearest star. To reach its extreme trajectory, NASA's engineers planned a series of 7 flybys of Venus, each one designed to siphon off a bit of the spacecraft's orbital energy. With every pass, Parker's path around the Sun became tighter and closer, allowing gravity to work its magic, turning potential energy into velocity in the purest way possible. The result? During its 2024 perihelion, the point where it is closest to the Sun, Parker reached a top speed of roughly 700,000 kilometers per hour. That's about 194 kilometers per second. To put that in perspective, at that speed, you could travel from New York to Tokyo in less than a minute, or circle the entire Earth in about 5 minutes. No other spacecraft, no other human-made object of any kind has ever come close. The conditions Parker endures at those speeds are nothing short of brutal. At its closest approach, it comes within about 6.2 million kilometers of the Sun's surface, inside the outermost layer of the corona, where temperatures can soar to more than 1,400 degrees Celsius or 2,550 degrees Fahrenheit. To survive such extremes, the probe is shielded by an advanced carbon composite heat shield just 11.4 centimeters thick, capable of withstanding direct exposure to the Sun's intense radiation while keeping its instruments at a comfortable room temperature. Behind this barrier, Parker's sensors measure the flow of charged particles, the structure of magnetic fields, and the dynamics of solar flares, a data that is revolutionizing our understanding of the Sun and space weather. What makes Parker's achievement even more remarkable is how long and carefully orchestrated its acceleration has been. Each of its Venus flybys acts like a cosmic brake, redirecting its orbital path rather than simply speeding it up. Yet paradoxically, every reduction in orbital radius leads to an increase in velocity relative to the Sun. It's the same principle that makes a figure skater spin faster when pulling in their arms, except Parker's arms span millions of kilometers and its dance partner is the Sun itself. At these astonishing speeds, the forces of space become surreal. Tiny particles of dust and plasma, harmless at ordinary velocities, strike Parker with the energy of bullets. Even sunlight behaves differently. Photons, the particles of light, bombard the probe with such intensity that they exert measurable pressure on its surface.
Every movement, every adjustment must be meticulously calculated because even the smallest mistake at 700,000 kilometers per hour can mean disaster. But for all its speed, Parker is also a lesson in patience. It will take years of orbits and gravity assists to complete its mission, each pass bringing it a little closer to the Sun, a little faster than before. By the end of its planned journey, NASA expects Parker to reach a final velocity of around 692 to 720,000 kilometers per hour, securing its legacy as the fastest object humanity has ever built, a title it will likely hold for decades to come. Yet perhaps the most astonishing part of the story isn't just the raw speed itself, but what it means. The Parker Solar Probe isn't chasing records for glory, it's chasing knowledge. By enduring the sun's fury, it's helping scientists understand phenomena that affect everything from solar storms to power grids on Earth. The data it sends back tells us how the sun breathes, how it ejects streams of charged particles that create auroras, disrupt satellites, and shape the boundaries of our solar system. Parker's speed also redefines how we perceive motion. At 700,000 kilometers per hour, it's traveling at nearly 0.064% of the speed of light, an astonishing figure that highlights both our technological triumphs and our cosmic humility. Even at its incredible pace, light, moving at 300,000 kilometers per second, would still race past Parker as if it were standing still. This comparison underscores just how vast and unyielding the scales of space are. Every time Parker swings past the sun, it carries with it the fingerprints of human ingenuity. It is a silent ambassador of our species' relentless drive to go faster, farther, and deeper into the unknown. Each data packet it transmits, each orbit it completes, is a reminder that speed is not just a number, it's a story of curiosity, risk, and endurance. From the relatively gentle journeys of Mercury capsules to the violent fury of solar flight, Parker's Solar Probe stands at the pinnacle of what we can achieve with current propulsion and engineering. It's the physical embodiment of a question that has driven explorers for centuries. How fast can we go?
And while Parker's record is astonishing, it also highlights something humbling, that even at nearly 750,000 kilometers per hour, we are still crawling compared to the speed of light. The next great leap in cosmic velocity will demand not just better engineering, but entirely new ideas about propulsion and energy itself. When you hear that NASA's Parker Solar Probe races through space at nearly 700,000 kilometers per hour, it feels almost beyond comprehension. That's fast enough to cross the continental United States in less than 30 seconds, or to reach the moon in just over half a day. It's a speed that defies human experience. Yet, in the vast arena of the cosmos, it's still almost nothing. Because when you compare Parker's record-breaking velocity to the ultimate speed limit of the universe, the speed of light, it suddenly seems like a gentle crawl. The speed of light, denoted by the constant c, is approximately 299,792 kilometers per second, about 1.08 billion kilometers per hour. That number is so enormous that it's almost abstract. Light can circle Earth 7.5 times in a single second. It takes only about 8 minutes for sunlight to travel the 150 million kilometers between the sun and Earth. In contrast, Parker Solar Probe, even at its peak velocity of 194 kilometers per second, covers that same distance in over 8 days. So while it's the fastest object ever built by humans, it's still moving at a mere 0.064% of light speed, less than 1/10 of 1%. To put that in more human terms, if flight were a race car blazing around a track at top speed, Parker would be like a jogger trying to keep up. Light would complete over 1,500 laps before Parker even finished one. Even more humbling, Voyager 1, humanity's most distant spacecraft, has been traveling through space for nearly half a century, yet it's still moving at only 0.006% of light speed. These comparisons highlight just how immense the speed of light truly is, and how vast the distances between stars really are. This enormous disparity between our fastest machines and light's incredible pace is more than just a fun fact.
It's a fundamental limitation written into the laws of physics. According to Einstein's theory of relativity, no object with mass can ever reach or exceed the speed of light. The closer something moves to that limit, the more energy it requires to keep accelerating. The curve is exponential. Double your speed, and the energy required doesn't double, it multiplies dramatically. To accelerate a single kilogram of mass to light speed would require infinite energy, something no technology, real or imagined, could ever provide. This isn't just a theoretical barrier. It's a practical one that defines the boundaries of what's physically possible. Even achieving a significant fraction of light speed, say 10% or 20%, would demand energy outputs that dwarf anything humanity can currently produce. For comparison, the total annual energy consumption of all human civilization wouldn't even come close to accelerating a modest spacecraft to 1/10 the speed of light. When viewed through that lens, Parker's achievement becomes even more remarkable. It represents the absolute pinnacle of what's possible using current propulsion methods, a triumph of gravity-assisted acceleration and precise engineering. Yet, it also shows how far we have to go before interstellar travel becomes realistic. The nearest star system, Alpha Centauri, lies about 4.37 light-years away. At light speed, that journey would take just over 4 years. At Parker's maximum velocity, it would take more than 6,700 years to make the trip. And even if we could somehow multiply Parker's speed tenfold, a feat far beyond our current capabilities, it would still take 670 years to reach the nearest star. And that's assuming we could maintain that speed continuously without slowing down or needing fuel. In essence, even our fastest spacecraft are like snails on the cosmic highway. However, this contrast between light speed and our mechanical speed isn't discouraging. It's inspiring. It reminds us that we are still at the beginning of our journey as a spacefaring species. Every record we break, every new speed we achieve, brings us a step closer to understanding what it would take to bridge the gap between planets and one day between stars. It's also worth noting that while we may be limited by the speed of light, photons, those tiny packets of light, are not just fast, they're the messengers of the universe. They carry information across billions of light years, allowing us to peer back in time and see galaxies as they were billions of years ago. For now, we rely on light to explore the cosmos, even if we can't travel at its speed. Our telescopes, like the James Webb Telescope, move information at light speed, letting us see cases our spacecraft may never reach. The Parker Solar Probe, therefore, sits at a fascinating intersection of human limitation and cosmic scale. It embodies both our greatest technological achievement and our greatest humility. At 700,000 kilometers per hour, it's blazing through the inner solar system faster than any human-made object ever has. But compared to light, the universe's true speed champion, it's still crawling. And that gap between Parker's speed and light speed is the distance between what's possible today and what might one day define our future. To bridge that gap, we'll need new forms of propulsion, technologies that go beyond chemical rockets and gravitational boosts. The next era of exploration will demand ion engines, solar sails, and perhaps even nuclear-powered or laser-driven craft capable of reaching a meaningful percentage of light speed. Until then, Parker's journey stands as both a victory and a challenge, a reminder that while we've learned to chase the sun, the stars still await.
Even before the Parker Solar Probe claimed its title as the fastest human-made object, several spacecraft blazed trails through the solar system, setting speed records that stood for decades and laying the groundwork for modern missions. Among them, Helios 2 and New Horizons stand as two of the most remarkable, both in the sheer velocity they achieved and in the clever use of celestial mechanics that made those speeds possible. Each mission, in its own era, pushed the boundaries of what was technologically conceivable and expanded our understanding of how to move efficiently and incredibly fast through the void. Let's start with Helios 2, launched on January 15, 1976, as part of a joint project between NASA and what was then West Germany's space agency. The goal of the Helios mission
was to study the sun up close, to investigate the properties of the solar wind, and to observe how the sun's radiation and magnetic fields behaved near its surface. Achieving this required venturing closer to the sun than any spacecraft had ever dared, a challenge that demanded extraordinary speed and precision. To get close to the sun, a spacecraft actually has to slow down relative to the sun, shedding much of the orbital velocity it inherited from Earth. But as it falls inward, pulled by the sun's immense gravity, it accelerates rapidly, gaining incredible speed during its closest approach. Helios 2 followed this principle to perfection. At its perihelion, just 43.4 million kilometers from the sun, closer than Mercury's orbit, it reached an astonishing velocity of 252,800 kilometers per hour, or 70.2 kilometers per second relative to the sun. For over 40 years, that number remained unbeaten, the fastest speed ever recorded for any human-made object. What's remarkable about Helios 2 is not just how fast it traveled, but how it endured the conditions near the sun. Temperatures soared to over 250 degrees Celsius, and the spacecraft had to be specially constructed to withstand the intense radiation and heat. Its instruments, including plasma detectors, magnetometers, and particle sensors, sent back invaluable data about solar activity, helping scientists understand the mechanisms behind solar flares, coronal mass ejections, and the solar wind that flows outward across the entire solar system. Helios 2 was a triumph of both engineering and orbital design. It didn't use gravity assists in the modern sense. That technique would become central in later missions, but it demonstrated how gravity itself, even without external boosts, could be harnessed to achieve phenomenal speeds. The spacecraft essentially fell toward the sun, trading altitude for momentum, and in doing so, it revealed how proximity to massive celestial bodies can act as natural accelerators. Decades later, another mission would take those principles to new heights, or rather, new distances. New Horizons, launched on January 19, 2006, was humanity's first mission to Pluto and the Kuiper Belt, a region of icy worlds and ancient remnants at the edge of our solar system. From its very beginning, New Horizons was built for speed. The spacecraft needed to travel nearly 5 billion kilometers to reach Pluto in a reasonable amount of time, so NASA designed one of the most powerful launch profiles ever executed. When New Horizons left Earth atop an Atlas V rocket, it blasted away from our planet at an initial velocity of 58,000 kilometers per hour, or 16.1 kilometers per second, the fastest launch speed ever achieved by a spacecraft departing Earth. It passed the Moon's orbit in just 9 hours, a journey that took Apollo astronauts 3 days. But that was only the beginning. To reach Pluto even faster, New Horizons performed a gravity assist maneuver at Jupiter in February 2007. By carefully flying through Jupiter's powerful gravitational field, the spacecraft effectively stole a tiny bit of the planet's orbital momentum, catapulting itself to even greater speeds, nearly 83,000 kilometers per hour or 23 kilometers per second relative to the sun. This gravitational slingshot shaved years off its travel time, allowing it to reach Pluto in just 9.5 years, arriving in July 2015. That Jupiter flyby didn't just provide speed, but it also gave scientists a bonus opportunity to study Jupiter's atmosphere, magnetosphere, and moons on the way. The maneuver exemplified one of the great insights of modern spaceflight. To go faster, use the gravity of other worlds. By approaching a massive planet and timing the trajectory perfectly, a spacecraft can convert part of the planet's orbital motion into its own, accelerating without burning additional fuel. This principle, first proven in missions like Pioneer and Voyager, is now the backbone of interplanetary navigation.
At its peak, New Horizons traveled so fast that it could cross the distance between Los Angeles and New York in under 3 minutes. Even more impressive, as it continued beyond Pluto and deeper into the Kuiper Belt, it maintained a velocity of over 50,000 kilometers per hour. Today, nearly 20 years after launch, it continues its voyage outward, carrying the fastest human farewell into the depths of space, a plaque and a message for whatever civilization, if any, might someday find it.
When you place Helios 2 and New Horizons side by side, you see two different philosophies of speed. Helios 2 achieved its incredible velocity by diving toward the sun, falling inward and letting gravity do the work. New Horizons, on the other hand, raced away from the sun, flung outward into the cold darkness by the combined force of its rocket and Jupiter's gravitational sling. One was a journey inward into heat and light. The other, a journey outward into cold and shadow. Yet both tell the same story, that mastering motion in space means mastering gravity itself. These missions are the reason we know how to send spacecraft anywhere in the solar system, not by brute force, but by cooperation with the natural rhythms of celestial motion. The careful dance of falling, turning, and slingshotting has allowed humanity to travel farther and faster than rocket engines alone ever could. In many ways, Helios 2 and New Horizons are spiritual predecessors to the Parker Solar Probe. The same fundamental principles that allowed Helios 2 to reach its extraordinary velocity now propel Parker through its record-breaking orbits. And New Horizons' mastery of the gravity assist remains one of the most elegant demonstrations of how to achieve near-limitless speed with finite fuel. But as these spacecrafts blaze through space, they also remind us that there's an upper ceiling to how much gravity alone can do. To go truly faster, to reach speeds approaching a meaningful fraction of light, we'll need to invent new forms of propulsion altogether. For now, though, missions like Helios 2, Voyager, and New Horizons stand as monuments to human creativity. Proof that with ingenuity, we can turn the motion of planets into cosmic highways and gravity itself into our greatest engine. One of the most elegant and ingenious tricks in all of space exploration, one that has allowed our spacecraft to reach astonishing speeds without burning vast amounts of fuel, is the gravity assist, also known as a slingshot maneuver. It's a technique so simple in principle, yet so powerful in execution, that it transformed what was once impossible into routine. Without it, missions like Voyager, Galileo, Cassini, New Horizons, and the Parker Solar Probe would never have reached their ambitious destinations, let alone set speed records that stretched the imagination. At its core, a gravity assist is the art of stealing a little bit of momentum from a planet as a spacecraft swings by it. Imagine throwing a ball past a moving train. If the ball passes close enough to the train and at just the right angle, the train's motion imparts a bit of extra energy to the ball, accelerating it forward. The train slows down by an imperceptible amount, but the ball speeds up dramatically. That's exactly what happens during a planetary flyby, except on a cosmic scale and with precision measured in fractions of a second. When a spacecraft approaches a planet, it falls into that planet's gravitational field. As it accelerates toward the planet, it gains kinetic energy, just as an object falling toward Earth does. If it were to pass straight by and continue on, it would leave with the same speed it entered, because gravity alone doesn't create energy. It only exchanges it. But when the spacecraft's trajectory is carefully angled relative to the planet's motion around the sun, something remarkable happens. The spacecraft picks up a bit of the planet's orbital momentum, effectively slingshotting forward with extra speed relative to the sun. Here's the key. The spacecraft's velocity changes relative to the sun, not just the planet. From the planet's frame of reference, the probe comes in and leaves with roughly the same speed. But because the planet itself is moving around the sun at tens of thousands of kilometers per hour, the spacecraft can leave the encounter with an added boost. It's like running along a moving walkway in an airport.
Your running speed stays the same, but relative to the building around you, you're moving much faster. For example, Jupiter, the largest planet in our solar system, moves around the Sun about 47,000 kilometers per hour. When a spacecraft like Voyager 1 flew past Jupiter in 1979, it approached the planet from behind, in the same direction the planet was traveling. Jupiter's immense gravity pulled Voyager toward it, accelerating the probe as it fell closer. As Voyager swung around the gas giant and exited on the far side, it was flung forward, having borrowed a fraction of Jupiter's orbital energy. The result was a speed increase of nearly 15 kilometers per second, over 54,000 kilometers per hour, completely free of charge. And here's the astonishing part. Even though Jupiter gave up that energy, it didn't noticeably slow down. The change in the planet's velocity was infinitesimally small, less than a billionth of a meter per second. In essence, Voyager robbed Jupiter of momentum, but the planet was so massive that it didn't even feel the loss. This is the beauty of the gravity assist, an exchange so efficient that the cost to the donor is imperceptible, but the gain to the traveler is enormous. Engineers and mission designers have learned to choreograph these flybys with breathtaking precision. Timing is everything. A spacecraft must arrive at just the right moment, at just the right angle, and at just the right distance from the planet to achieve the desired effect. Arrive too early or too late, and the planet won't be in position. Miss the angle by even a few degrees, and the trajectory could send the probe hurtling off into deep space, never to return. The Voyager missions were the first to fully exploit the celestial slingshot technique in what NASA called the Grand Tour, a rare alignment of the outer planets that happens only once every 175 years. By flying past Jupiter, Saturn, Uranus, and Neptune in sequence, each encounter propelled the spacecraft toward the next, using no additional fuel beyond small course corrections. Voyager 1 and 2 used this natural choreography to escape the solar system entirely, becoming the most distant human-made objects ever. Since then, the gravity assist has become a standard tool of interplanetary navigation. The Galileo mission to Jupiter in the 1990s used flybys of Earth and Venus to build up speed before heading toward its final destination. The Cassini spacecraft used multiple Venus flybys as well as a final swing around Earth to gain the necessary momentum to reach Saturn. New Horizons, as we discussed earlier, used a precisely timed pass by Jupiter to shave years off its journey to Pluto. Even the Parker Solar Probe, despite its mission to the inner solar system, relies on gravity assist from Venus, not to speed up, but to slow down and lower its orbit toward the Sun. This dual nature of gravity assists, that they can both accelerate and decelerate depending on the desired outcome, makes them one of the most versatile tools in space travel. When a spacecraft needs to reach the outer planets quickly, it passes behind a moving planet to gain energy. When it needs to fall inward toward the Sun or an inner planet, it passes ahead of a planet, allowing gravity to pull it backward, stealing some of its speed and lowering its orbit. From a fuel efficiency standpoint, gravity assists are nothing short of miraculous. Traditional rocket propulsion is limited by the amount of fuel a spacecraft can carry, and every extra kilogram of fuel adds more weight, which in turn requires even more fuel to launch. Gravity assists sidestep that problem entirely. Once a spacecraft is on its path, it can use the natural motion of planets as an interplanetary highway system, trading careful navigation for incredible speed.
It's not an exaggeration to say that gravity assists are what make modern space exploration possible. Without them, the Voyager probes would have required enormous rockets the size of skyscrapers and decades longer to reach the same destinations. Cassini and Galileo might never have reached their targets. Even New Horizons would have taken twice as long to reach Pluto. The concept turns the solar system itself into an engine, one that runs forever, requiring no fuel and obeying only the laws of motion. What's even more poetic is that this technique, this mastery of celestial momentum, mirrors the very dance of the cosmos.
Planets, moons, and asteroids constantly exchange energy through their gravitational interactions, subtly shaping orbits and trajectories across billions of years. By using gravity assists, humanity has learned to join that dance, harnessing the same forces that have guided worlds since the dawn of time. And as we look to the future, to missions beyond our solar system, to interstellar travel, the gravity assist will remain a crucial stepping stone. It's not just a clever trick, it's proof that speed in space doesn't always come from power, but from wisdom, from understanding how to work with the universe instead of against it. Yet, even gravity has its limits. There's only so much energy we can borrow from planets, and at some point, the vast distances between stars demand new kinds of propulsion, engines that don't just steal motion, but create it. Before we can dream of such technologies, though, we must understand the barriers that hold this back, the propulsion limits that define how fast we can currently go. Even though gravity assists have allowed us to travel faster and farther than rocket fuel alone ever could, they can only take us so far. To truly understand the speed limits of space travel today, we need to look at what actually propels our spacecraft, the engines themselves. And at the heart of nearly every space mission to date lies a technology that has served humanity for over a century: chemical rockets. They've taken us to orbit, to the moon, and even sent probes beyond the solar system. Yet they also represent one of the biggest bottlenecks to how fast we can go. Chemical propulsion is powerful, but it's fundamentally constrained by physics. Rockets operate on Newton's third law of motion. For every action, there's an equal and opposite reaction. When a rocket burns fuel and expels exhaust gases downward at high speed, it produces an equal force upward, propelling the spacecraft forward. The faster the exhaust gases are expelled, and the more mass that's ejected, the more thrust the rocket can generate. But that thrust comes at a steep cost. It requires enormous amounts of fuel. The main metric that defines rocket performance is something called specific impulse, ISP. It measures how efficiently a rocket uses its fuel, essentially how much thrust it produces per unit of propellant. Most chemical rockets have a specific impulse in the range of 250 to 450 seconds, depending on the fuel type and engine design. For example, solid fuel rockets like those used in boosters have lower efficiency, while liquid hydrogen and liquid oxygen engines like NASA's RS-25 engines that powered the space shuttle are among the most efficient chemical rockets ever built. That might sound impressive, but in the cosmic sense, it's painfully limited. The reason is that to go faster, you need exponentially more fuel. This is captured perfectly by the Tsiolkovsky rocket equation, which states that the change in velocity a rocket can achieve, its delta V, depends on the exhaust velocity of its fuel and the ratio between the rocket's starting mass, including fuel, and its final mass after the fuel is burned. The equation is brutally unforgiving. To double your speed, you don't just need twice the fuel, you might need 10 times as much. This exponential relationship creates what's often called the tyranny of the rocket equation. For missions that need to escape Earth's gravity well, most of the rocket's weight at launch is just fuel, not cargo, not equipment, not astronauts. In fact, over 85 to 90% of a launch vehicle's total mass is fuel. By the time a spacecraft reaches orbit, almost all that fuel has been spent just fighting gravity and atmospheric drag. What's left to propel the spacecraft deeper into space is a fraction of what it started with. And that's why achieving high velocities with chemical propulsion alone is so difficult. Let's put this into perspective. Earth's escape velocity is about 11.2 kilometers per second, roughly 40,000 kilometers per hour. That's the speed needed to break free from Earth's gravity completely. The Saturn V rocket, which launched the Apollo missions, achieved this using an incredible 34 million newtons of thrust, burning through over 2,700 tons of fuel in just a few minutes. Yet, even that immense power only got the Apollo spacecraft to around 39,000 kilometers per hour. To reach speeds 10 or 100 times greater, enough to travel to Mars in weeks instead of months, or to nearby stars in centuries instead of millennia, we would need fuel and engines far beyond anything chemical propulsion can provide. The main problem isn't just energy, it's efficiency. Chemical reactions can only release so much energy per kilogram of fuel because they're limited by the bonds between atoms and molecules. Even the most energetic chemical propellants, such as hydrogen-oxygen or exotic mixtures like fluorine-hydrazine, top out at around 4.5 kilometers per second exhaust velocity. In comparison, to reach a meaningful fraction of the speed of light, you'd need thousands of times greater exhaust velocity. That's simply impossible with chemistry alone. This limitation becomes especially apparent when you think about intraplanetary and interstellar distances. For instance, using current chemical rockets, it takes around 6 to 9 months to reach Mars when the planets are properly aligned. A journey to Jupiter might take 5 to 6 years, and to Pluto, even with gravity assists, nearly a decade. If we wanted to reach Proxima Centauri, the nearest star beyond our sun, it would take over 70,000 years at the speed of the fastest spacecraft we've ever built. Clearly, if humanity hopes to explore beyond our solar system, we need something more. Another issue with chemical rockets is that their thrust, while powerful, doesn't last long. They burn their fuel quickly, sometimes in just a few minutes or hours, and then coast the rest of the way through space. Once the fuel is gone, the spacecraft has no way to keep accelerating. That's why many missions depend on careful planning, using planetary alignments and gravity assist to make the most of that short-lived burst of energy. And there's also the issue of mass ratios. To achieve high speeds, a spacecraft must carry enormous fuel reserves, but carrying more fuel adds weight, which in turn requires more fuel to lift that extra weight, a vicious cycle that engineers constantly battle. This is why multi-stage rockets were invented. Each stage carries its own fuel and engines, and once it's spent, it's discarded to lighten the load for the next stage. The Saturn V, for example, had 3 stages, each one shedding dead weight as it climbed higher, allowing the final stage to propel the Apollo capsule toward the moon.
Despite these challenges, chemical rockets have achieved incredible feats. They remain the only technology capable of lifting heavy payloads off Earth and sending them into orbit or beyond. The SpaceX Falcon Heavy, NASA's SLS, and the Ariane 6 all rely on chemical propulsion because of its high thrust-to-weight ratio, something no other propulsion method can yet match. When you need to overcome gravity and launch from a planet's surface, nothing beats raw chemical power. But in the vacuum of space, where you're not fighting atmospheric drag or gravity wells, raw power isn't as important as efficiency and endurance. That's where chemical propulsion starts to show its age. Once you're in orbit, the best way to go faster isn't by firing big rockets. It's by finding propulsion systems that can accelerate slowly but steadily over long periods. This realization is what led engineers and scientists to look beyond chemistry and explore advanced propulsion methods, systems that rely on electricity, magnetism, or even nuclear reactions to generate thrust. Unlike chemical rockets, these engines can operate continuously for months or even years, gradually building up enormous speeds. So while chemical propulsion has brought us this far, from the first steps into orbit to the edges of our solar system, it's also the barrier holding us back from going farther. It's the foundation of our achievements, but also the ceiling of our speed. To break through that ceiling, we have to think differently, not about brute force, but about smarter, more efficient propulsion technologies that could one day make interplanetary travel routine and interstellar travel possible. If chemical rockets represent the brute strength of early spaceflight, the muscle that got us off Earth, then advanced propulsion technologies represent its mind and imagination. As we look beyond our current limitations, scientists and engineers have begun developing and testing new propulsion systems that rely on principles far more subtle and elegant than burning fuel. These emerging technologies, ion drives, nuclear propulsion, and solar sails, promise not just higher efficiency, but a fundamental shift in how we think about motion through space. They won't get us to other stars overnight, but they could one day make interplanetary travel faster, cheaper, and far more sustainable than it is today.
Let's start with one of the most mature and proven of these technologies, the ion drive or ion propulsion system. Unlike chemical rockets, which rely on explosive combustion, ion engines use electricity, often generated by solar panels, to accelerate charged particles, ions, to extremely high speeds. The principle is simple but brilliant. Electricity strips electrons from atoms of a propellant, usually xenon gas, creating positive ions. These ions are then accelerated out of the engine using electromagnetic fields, producing a gentle but continuous thrust. At first glance, ion propulsion might seem unimpressive. Its thrust is so weak that you could barely feel it if you held an operating ion thruster in your hand. It exerts about as much force as the weight of a sheet of paper. But here's the secret. That thrust never stops. Whereas chemical rockets burn furiously for a few minutes, ion drives can keep firing for months or even years, gradually building up tremendous velocity. Because of their incredible efficiency, ion engines boast specific impulses of 3,000 to 10,000 seconds, 10 to 20 times better than chemical rockets. That means they can achieve far higher final speeds using only a fraction of the fuel. The NASA Dawn mission, which explored the asteroid belt between Mars and Jupiter, was a perfect demonstration of this. Powered by 3 xenon ion engines, Dawn traveled over 6.9 billion kilometers during its mission, orbiting both Vesta and Ceres, something no spacecraft had ever done before. Over its 11 years of operation, it reached speeds exceeding 40,000 kilometers per hour, propelled by a total of just 425 kilograms of xenon. Another example is ESA's BepiColombo mission to Mercury. Launched in 2018, it uses advanced ion propulsion to slowly spiral inward toward the Sun, performing multiple flybys of Earth, Venus, and Mercury to adjust its orbit. Without ion propulsion, the mission's complex trajectory would have been impossible. These systems are redefining what slow and steady wins the race means in space exploration. Yet even ion propulsion has its limits. It requires large amounts of electricity, which means big solar arrays or other power sources. In the outer solar system, where sunlight is weak, this becomes a problem. That's why researchers are exploring propulsion systems that draw power not from the sun, but from the nucleus of the atom, systems like nuclear thermal and nuclear electric propulsion. Nuclear thermal propulsion, or NTP, works on a simple idea. Replace chemical combustion with nuclear fission. Instead of burning fuel, a reactor heats up a propellant like liquid hydrogen to extremely high temperatures, then expels it through a nozzle to create thrust. Because nuclear reactions are vastly more energy-dense than chemical ones, an NTP engine could achieve exhaust velocities twice as high as the best chemical rockets, meaning it could cut travel times to Mars by half. A journey that currently takes 6 to 9 months might be reduced to 3 or 4 months. NASA and the U.S. Department of Defense are currently working on experimental nuclear propulsion systems with a mission called DRACO, Demonstration Rocket for Agile Cislunar Operations, expected to test a small nuclear thermal engine in space by the late 2020s. If successful, it could pave the way for crewed missions to Mars and beyond, with faster travel, shorter exposure to radiation, and more flexible mission designs. Then there's nuclear electric propulsion, which combines the strengths of both nuclear and ion systems. In nuclear electric propulsion, a reactor doesn't directly heat a propellant. Instead, it generates electricity, which powers high-efficiency ion or plasma thrusters. This method offers the efficiency of electric propulsion with the immense, long-lasting power of nuclear energy. Such a system could theoretically operate for years or decades, making it ideal for deep space exploration and interstellar probes. And if nuclear power sounds futuristic, it's actually rooted in ideas that date back to the 1960s. Projects like NERVA, Nuclear Engine for Rocket Vehicle Application, demonstrated working nuclear thermal rockets on Earth decades ago, though safety concerns kept them grounded. Today, with renewed interest in Mars and beyond, these once-shelved technologies are finally returning to the spotlight.
But among all the propulsion concepts under exploration, perhaps the most poetic is the solar sail, a technology that doesn't rely on fuel at all. Instead, it uses the pressure of sunlight itself to push a spacecraft forward. While photons, particles of light, have no mass, they do carry momentum. When they strike a reflective surface, they impart a tiny push, so small it's almost imperceptible, yet constant.
Over time, this gentle pressure can accelerate a lightweight spacecraft to incredible speeds. Solar sails are essentially enormous mirror-like sheets of material, often thinner than human hair, that unfold in space to capture sunlight. The Icaro spacecraft, launched by Japan's space agency JAXA in 2010, was the first successful demonstration of this technology. Its 14-meter-wide sail used solar radiation to accelerate continuously, eventually reaching speeds of over 360 kilometers per hour relative to Earth without a drop of fuel. Another mission, LightSail 2, developed by the Planetary Society and launched in 2019, showed that even small spacecraft could use sunlight to change their orbits. By tilting its reflective panels, LightSail 2 could control the direction of its acceleration, essentially tacking through space the same way a sailboat uses wind on the ocean. The success of LightSail proved that photon propulsion wasn't just a fantasy, it's a working, scalable technology. The true promise of solar sails, however, lies in their potential for interstellar travel. Projects like Breakthrough Starshot, supported by Stephen Hawking and other scientists, envision using powerful ground-based lasers to push miniature, sail-equipped probes to speeds approaching 20% the speed of light. At such velocities, these tiny spacecraft could reach Proxima Centauri, our nearest neighboring star, in just over 20 years, an unimaginable leap from today's technology. Of course, challenges remain. Building lightweight yet durable sails, aiming high-energy lasers with incredible precision, and surviving interstellar dust at relativistic speeds. But conceptually, solar sails demonstrate a future where propulsion doesn't mean burning fuel, it means mastering light itself. Each of these technologies, ion drives, nuclear propulsion, and solar sails, represents a different answer to the same question. How do we keep going faster, longer, and farther without being chained to the tyranny of rocket fuel? And while none are perfect, together they form a roadmap toward a new era of space exploration. An era where spacecraft are no longer limited by explosive chemistry, but empowered by the fundamental forces of nature: electricity, atomic energy, and light. These innovations are not just theoretical. Some are already flying, others are under active development. And as we'll see next, a few, like ion engines, are already proving their worth in real missions across the solar system. Ion propulsion, once the stuff of science fiction, is now quietly redefining how we move through the solar system. It doesn't roar like a chemical rocket or create blinding flames, instead it whispers, pushing with the soft persistence of sunlight over months and years. Yet, despite its gentleness, this technology has already carried spacecraft across billions of kilometers, orbiting asteroids, visiting planets, and reshaping our vision of what fast really means in the cosmos. To understand how, we can look closely at two remarkable missions: NASA's Dawn spacecraft and ESA's BepiColombo mission to Mercury. Ion propulsion works on a very different philosophy from chemical rockets. Instead of delivering a powerful burst of acceleration in a few minutes, ion engines generate a tiny but continuous thrust, so small that it wouldn't even lift a piece of paper on Earth. But in the frictionless vacuum of space, where there's no air resistance or drag, that minuscule thrust compounds relentlessly. Over time, this constant push can accelerate a spacecraft to speeds far greater than any chemical engine could ever sustain. The Dawn mission, launched in 2007, is perhaps the best real-world demonstration of this principle. Dawn's mission was to explore two of the largest objects in the asteroid belt, Vesta and Ceres, both remnants from the early formation of the solar system. To do this, it needed to not just visit them, but actually enter orbit around both, an unprecedented feat. With conventional propulsion, this would have been impossible, but Dawn's ion engines made it achievable. The spacecraft was equipped with 3 ion thrusters, powered by solar energy. Each thruster used xenon gas as its propellant, a noble gas that, when ionized and accelerated through an electric field, produced a bluish exhaust of charged particles moving at up to 40 kilometers per second. The result was an incredibly efficient propulsion system with a specific impulse of around 3,100 seconds, roughly 10 times better than a high-performance chemical rocket. At full power, Dawn's engines generated just 90 millinewtons of thrust, equivalent to the weight of a single sheet of paper resting on your palm. But this tiny push was unrelenting. When operated continuously for weeks, months, or even years, it added up to enormous changes in velocity. Over the course of its mission, Dawn's ion engines fired for a total of 2,141 days, nearly 6 years of cumulative thrusting, and changed the spacecraft's speed by more than 10 kilometers per second. That's faster than the top speed of the Apollo missions on their way to the moon, achieved with far less propellant. The beauty of ion propulsion is in that trade-off between slow acceleration and eventual high velocity. It's a marathoner, not a sprinter.
In the first few days after firing its engines, Dawn's motion was almost imperceptible. But after a few months, it was traveling tens of thousands of kilometers per hour faster than before. After a year, the change was staggering. What makes this so powerful is that ion engines don't run out of fuel quickly. A few hundred kilograms of xenon can last for years. Dawn's entire supply of 425 kilograms propelled it across the asteroid belt, into orbit around Vesta, out again, and then into orbit around Ceres, the only spacecraft in history to orbit 2 extraterrestrial bodies.
Beyond its technical achievements, Dawn's ion propulsion also symbolized a new way of exploring space, one that's not limited by brute force, but by patience and precision. Every day, its gentle thrust subtly reshaped its orbit, steering it like a cosmic sailboat across the gravitational currents of the inner solar system. It wasn't fast in the cinematic sense. There were no dramatic bursts or flaming trails, but its steady persistence made it one of the most efficient travelers in human history. While Dawn was pioneering the technique in the asteroid belt, another spacecraft, ESA's BepiColombo mission, began using a similar principle to tackle one of the hardest destinations in the solar system, Mercury. Launched in October 2018 as a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, BepiColombo's goal is to study Mercury's surface, magnetic field, and exosphere in unprecedented detail. But reaching Mercury is no simple feat. Unlike missions heading outward from the Sun, journeys inward require spacecraft to slow down, not speed up. That's because any object starting from Earth is already moving at about 30 kilometers per second relative to the Sun. To match Mercury's much slower orbital speed of around 47 kilometers per second, a spacecraft must shed enormous amounts of energy, essentially falling inward while constantly fighting to avoid being pulled too fast into the Sun. That's where ion propulsion comes in. BepiColombo uses 4 T6 ion thrusters, each developed by Kinetic in the UK, powered by large solar panels generating up to 14 kilowatts of electricity. These engines can run continuously for months at a time, gradually adjusting the spacecraft's trajectory and velocity. The mission's journey to Mercury involves a complex sequence of 9 planetary flybys, 1 at Earth, 2 at Venus, and 6 at Mercury itself, all coordinated with long periods of ion-powered thrust. This combination of gravitational navigation and continuous low-thrust propulsion makes BepiColombo one of the most precisely engineered space journeys ever attempted. Its engines are so efficient that, despite traveling over 9 billion kilometers, the spacecraft carries only about 600 kilograms of xenon as propellant. It's expected to finally enter Mercury's orbit in 2026, after an 8-year voyage, a journey made possible only through the endurance and adaptability of ion propulsion. Ion propulsion strengths are clear. It provides tremendous fuel efficiency, long operational lifespans, and the ability to perform complex orbital maneuvers that chemical rockets could never sustain. But it also comes with notable limitations. The biggest is thrust. Ion engines simply can't generate the raw power needed to launch from a planet's surface or make rapid changes in trajectory. They're like efficient electric cars that can drive for years, but only if you already start them on a highway. That's why chemical rockets are still essential for launches, and ion engines take over only once a spacecraft is in the vacuum of space. Another challenge is power. Ion engines depend on electricity, which means their performance decreases as they move farther from the Sun. For missions beyond Jupiter, where sunlight is weak, engineers must rely on either massive solar panels or nuclear power sources, solutions that add complexity and cost. Despite this, the potential of ion propulsion is undeniable. It represents the first step toward a future where spacecraft don't sprint, but glide, propelled by intelligence, efficiency, and time. The lessons learned from Dawn and BepiColombo are shaping the next generation of missions. Future deep space explorers, from asteroid miners to Mars cargo ships, may use fleets of ion-powered craft capable of crossing the solar system on a fraction of the fuel we use today. NASA's upcoming Psyche mission, targeting a metal-rich asteroid, is also using solar electric propulsion, building directly on Dawn's legacy. Ion propulsion has proven that slow and steady doesn't just win the race, it redefines it. By turning patience into speed, it opens a new frontier of travel where endurance replaces explosiveness and precision replaces brute force. And yet, while robotic missions thrive under these conditions, human spaceflight faces a different challenge. Crewed missions demand higher safety margins, faster transit times, and systems capable of supporting life. That difference sets the stage for the next great comparison: the speed limits of humans versus robotic spacecraft. When we compare the astonishing velocities of robotic spacecraft like the Parker Solar Probe or New Horizons to the much slower pace of human missions, one question naturally arises: why can't we send humans as fast as our machines? After all, both use rockets, both navigate through the same vacuum of space, and both obey the same physical laws. The difference comes down to one thing: fragility. Robots can endure extremes that human beings cannot. Our need for safety, life support, and stability place profound limits on how fast we can currently travel through the cosmos. Robotic spacecraft are built for performance. They can tolerate intense heat, radiation, vibration, and acceleration that would instantly kill a person. When engineers design a probe like the Parker Solar Probe, they can focus entirely on the mission's scientific and technical requirements, pushing the hardware to the edge of endurance. Every gram of mass can be devoted to shielding, instruments, and propulsion. There's no need for food, oxygen, or radiation protection for living tissue. This freedom allows robotic spacecraft to achieve incredible velocities, often by taking trajectories that would be far too dangerous or uncomfortable for humans. Human missions, on the other hand, are built around life support and survival. Every crewed mission must maintain a stable, livable environment, regulating temperature, pressure, oxygen, and waste systems. It must shield astronauts from cosmic radiation, micrometeorite impacts, and the vacuum of space. The more we protect the crew, the more mass we add. And as mass increases, the speed we can achieve with a given amount of fuel decreases. The rocket equation is unforgiving. Every extra kilogram of air, water, or shielding demands exponentially more propellant to accelerate.
Consider the Apollo missions, still the fastest human journeys ever undertaken. The Apollo 10 command module reached a top speed of about 39,897 kilometers per hour, or 24,791 miles per hour, during its return to Earth from lunar orbit. That's roughly 11 kilometers per second, fast enough to cross the continental United States in under 5 minutes. But compared to uncrewed spacecraft, like the Parker Solar Probe, which travels over 700,000 kilometers per hour, this is barely a crawl. Why is such a huge difference? Because Apollo had to keep its crew alive and safe. The spacecraft needed thick heat shields, reliable reentry systems, and careful trajectory planning to ensure that the astronauts could survive both the vacuum of space and the inferno of Earth's atmosphere upon return. Even before launch, human missions face strict acceleration limits. The human body can only withstand a certain amount of G-force, the stress caused by acceleration, before losing consciousness or sustaining injury. Trained astronauts can tolerate short bursts of up to 8 or 9 Gs, 8 or 9 times the force of gravity, during emergency reentry maneuvers. But prolonged exposure to even 3 or 4 Gs can cause vision problems, confusion, or blackout. Robotic spacecraft, in contrast, can handle accelerations dozens or even hundreds of times greater. This means a probe can perform high-speed slingshot maneuvers or powerful engine burns that would crush a human crew. Safety constraints also affect trajectory design. Crewed missions tend to follow more gradual, energy-efficient routes to minimize radiation exposure and reduce the risk of collision or overheating. Robotic spacecraft, however, can take riskier paths that pass close to the sun or through high radiation zones, trading danger for speed. For example, the Parker Solar Probe flies repeatedly through the sun's corona, a region with temperatures exceeding 1,000,000 degrees Celsius, shielded by a carbon composite heat shield that no human spacecraft could ever survive behind. Then there's the question of radiation. Outside Earth's magnetic field, astronauts are exposed to a constant bombardment of cosmic rays and solar particles.
Even on a journey to Mars, radiation levels are high enough to increase cancer risks and cause long-term damage to DNA and the central nervous system. Traveling faster would help reduce the time astronauts spend exposed to these hazards, but paradoxically, achieving those higher speeds would require either far more energy, which increases engineering complexity and cost, or trajectories that expose crews to even more radiation. It's a delicate balance. Go too slow, and radiation accumulates. Go too fast, and you risk destroying the spacecraft or exhausting fuel reserves before reaching your destination. Life support systems are another major speed-limiting factor. A robotic spacecraft is self-contained and passive. It can be turned off, powered down, or left drifting for years with no consequence. A crewed ship, however, must actively maintain life every second of its journey. That means constant power for air circulation, temperature control, and communication. It also means carrying or generating large quantities of food, water, and oxygen, all of which add to the spacecraft's mass and slow it down. Designing a human spacecraft is thus a balancing act between speed, safety, and sustainability. Engineers must decide how much risk is acceptable and how much redundancy is required to guarantee crew survival. That's why missions like Artemis or future Mars expeditions focus more on reliability and protection than sheer velocity. The priority isn't to arrive first, it's to arrive alive. Compare this to robotic missions like Voyager 1 launched in 1977. Voyager didn't need to worry about crew comfort or radiation doses. It used a combination of Jupiter and Saturn gravity assist to slingshot itself out of the solar system entirely, reaching speeds over 61,000 kilometers per hour. Even at that incredible pace, it took more than 35 years to reach the boundary of interstellar space. A human version of Voyager would have been impossible with today's technology. The radiation, isolation, and time would be insurmountable. Another example is New Horizons, which sped past Pluto in 2015. It launched at over 58,000 kilometers per hour, the fastest departure speed from Earth ever achieved. But if humans were aboard, such an intense acceleration would have been dangerous. The G-forces from that launch profile were tolerable only because there was no crew to protect. In contrast, human-rated rockets like the Space Launch System, SLS, or Falcon 9 Crew Dragon are designed with much gentler acceleration curves, rarely exceeding 3 Gs during ascent, ensuring the astronauts remain conscious and functional. There's also a philosophical difference between crewed and robotic missions. Robots can fail. Humans cannot. If a probe malfunctions, it's a loss of hardware and data. Unfortunate, but recoverable. If a human spacecraft fails, lives are lost. That distinction drives engineers to build crewed missions with multiple fail-safes, redundancies, and conservative flight plans. Every system must be tested to near perfection, every variable accounted for. The result is a spacecraft that's safer but slower, optimized for survival, not for speed. As technology advances, the gap between robotic and human speed limits may begin to close. More efficient propulsion systems, better radiation shielding, and improved life support might one day allow human missions to travel faster and farther. Nuclear propulsion, for example, might shorten the trip to Mars from 9 months to 3, reducing exposure and risk. But even then, safety will remain the ultimate governor of speed. In essence, robotic spacecraft are the sprinters, free to risk everything for velocity, while human missions are the marathon runners, pacing themselves carefully to ensure they make it to the finish line. Both approaches are vital. Robots extend our reach into dangerous and distant realms, paving the way for humans to follow when it's safe. And humans bring purpose, creativity, and adaptability, qualities machines still lack.
As we continue to explore the solar system, we'll need both. But understanding why our machines can travel so much faster than we can reminds us of the unique challenge of crewed exploration. In space, the limiting factor isn't technology alone, it's biology. When we look to the future of space exploration, one of the most compelling goals is simple yet profound: to go faster. Faster travel means reaching distant worlds in less time, reducing mission risks and opening the door to deeper exploration of our solar system and eventually the stars beyond. While current human and robotic missions are limited by the physics of propulsion and the practicalities of engineering, the next generation of spacecraft aims to push those limits further than ever before. From upcoming Mars missions to experimental deep space probes, the quest for speed is entering a new era, one defined by innovation, bold design, and a willingness to rethink how we move through space. Let's start with the most immediate target, Mars. For decades, Mars has been the holy grail of human exploration. Close enough to reach within a human lifetime, yet far enough to challenge every technological boundary we have. The typical journey from Earth to Mars using current propulsion methods takes 6 to 9 months depending on orbital alignment. That's a long time for astronauts to spend in microgravity, exposed to radiation, and isolated millions of kilometers from home. Reducing that travel time isn't just a convenience, it's a matter of safety and survival. NASA, SpaceX, and several international partners are all investigating ways to shorten the trip. SpaceX's Starship, for example, is designed with a fully reusable structure and massive payload capacity, capable of carrying both cargo and crew to Mars. While its primary propulsion still relies on chemical rockets, specifically methane-fueled Raptor engines, its efficiency and scale could make interplanetary travel more practical and faster by optimizing launch windows and orbital transfers. Elon Musk has often spoken about future upgrades that could allow Starship to reach Mars in as little as 80 days, potentially less with advanced trajectories or in-space refueling. NASA is taking a different approach by developing nuclear-powered propulsion systems, which could revolutionize deep space travel. One of the most promising concepts is nuclear thermal propulsion. This technology uses a small nuclear reactor to heat hydrogen propellant to extremely high temperatures, expelling it through a nozzle to generate thrust. The result is a system that's about twice as efficient as today's best chemical rockets. That means spacecraft using NTP could cut Mars travel time nearly in half, down to 3 or 4 months, while carrying heavier payloads and offering greater mission flexibility. A step beyond that is nuclear electric propulsion, which converts nuclear energy into electricity to power ion or plasma engines. This approach provides less thrust but much higher efficiency, allowing for continuous acceleration over long periods. NEP systems could one day propel massive interplanetary ships, perhaps even permanent human habitats traveling between planets, at speeds far beyond what's currently possible. NASA's DARCO project, demonstration rocket for agile cislunar operations, developed in partnership with DARPA, aims to test an early form of nuclear thermal propulsion in orbit by the late 2020s, potentially laying the groundwork for human missions to Mars in the 2030s. But Mars isn't the only destination where speed matters. Robotic missions heading deeper into the solar system are also being designed to move faster and travel farther than their predecessors. One ambitious example is NASA's Interstellar probe concept, a mission still in the proposal stage, but one that would aim to travel well beyond the boundaries of our solar system into interstellar space. Using powerful chemical rockets and a Jupiter gravity assist, this spacecraft could achieve speeds of up to 95,000 kilometers per hour, eventually surpassing even the legendary Voyager 1 in its journey beyond the heliosphere. To reach such high velocities, engineers are exploring solar sail technology, an elegant method that harnesses the pressure of sunlight itself as propulsion. Solar sails work by reflecting photons from the sun, creating a tiny but constant push. Over time, this push can accelerate a spacecraft to remarkable speeds without using any fuel. The Planetary Society's LightSail 2, launched in 2019, demonstrated this principle in Earth orbit, successfully changing its trajectory using sunlight alone. Future versions, on a much larger scale, could travel to Mars or the outer planets with no fuel expenditure at all. One particularly exciting proposal comes from NASA's Solar Cruiser mission, planned for the late 2020s. With a sail nearly 1,700 square meters in size, about half the area of a football field, it will be one of the largest solar sails ever deployed. This mission will test how effectively solar sails can maneuver and accelerate in deep space, paving the way for future high-speed, long-duration missions that rely purely on solar radiation pressure. Beyond solar sails, researchers are investigating fusion propulsion, a potential game-changer for interplanetary travel. Fusion, the same process that powers the sun, could provide immense thrust and efficiency, enabling spacecraft to reach Mars in weeks instead of months. Concepts like the direct fusion drive, under development at Princeton Satellite Systems, propose using small, contained fusion reactions to heat plasma and generate thrust. Though still in the experimental stage, this technology could offer specific impulses thousands of times higher than chemical rockets, turning interplanetary travel into something closer to intercontinental flight in speed and practicality. If successful, fusion drives might make missions to the outer planets, Jupiter, Saturn, and beyond, far more feasible. Imagine reaching Saturn in a year, or Neptune in under 5, rather than the decades it currently takes. Missions like Voyager 2 and New Horizons required elaborate gravity assists and years of travel to reach their targets. Fusion propulsion could bypass those limitations entirely, sending probes on direct, high-speed trajectories. Private companies and international agencies are also getting involved in the race for faster space travel. The European Space Agency, ESA, has studied hybrid propulsion systems, combining chemical and electric engines to optimize performance during different mission phases. Blue Origin has expressed interest in nuclear-based propulsion for future deep space missions. Meanwhile, China's space program is advancing its own plans for faster robotic probes, including proposed missions to Jupiter and Uranus that would use gravity assists and solar electric propulsion to cover billions of kilometers more efficiently than ever before.
As exciting as these technologies are, it's important to note that each comes with formidable challenges. Nuclear propulsion raises concerns about safety and containment, especially during launch. Fusion propulsion is still theoretical, requiring breakthroughs in plasma confinement and energy output. Solar sails, while elegant, depend heavily on proximity to the sun and precise navigation control. And for human missions, even with faster engines, radiation, microgravity, and psychological factors remain major hurdles. Still, the drive to go faster continues to shape the future of space exploration. Every new mission tests not only our technology, but also our imagination, pushing the boundary between what's currently possible and what might one day be routine. Faster travel times mean more ambitious missions, crewed Mars bases, asteroid mining operations, and possibly even interstellar precursors, spacecraft designed to leave the solar system entirely within a human lifetime. What's remarkable is that the pursuit of speed isn't just about reaching distant places more quickly. It's about expanding human presence in space, making exploration sustainable, efficient, and continuous. Each improvement in propulsion doesn't just shorten a trip, it expands what humanity can achieve, turning the vast distances of space into challenges that can eventually be overcome. And beyond even these future goals lies the next great leap. Not just traveling within our solar system, but venturing beyond it. That's where the next frontier awaits, the dream of interstellar travel, where humanity aims to bridge the unimaginable gulf between the stars themselves. The dream of reaching the stars has always stood as the ultimate symbol of human curiosity and ambition. The idea that one day we might cross the vast gulf between our sun and another. Until recently, this goal seemed purely the realm of science fiction, an unreachable fantasy given the staggering distances involved. The nearest star system, Alpha Centauri, lies about 4.37 light-years away, roughly 41 trillion kilometers. Even our fastest spacecraft, like the Parker Solar Probe, moving at over 700,000 kilometers per hour, would take more than 6,500 years to get there. But modern science,
driven by both daring imagination and engineering innovation, has begun to ask, what if we could go faster? What if we could send something, not a person, but a machine, to another star within a single human lifetime? This bold question forms the foundation of interstellar ambitions, and one of the most exciting projects attempting to answer it is Breakthrough Starshot. Announced in 2016 by physicist Stephen Hawking, venture capitalist Yuri Milner, and other scientific luminaries, Breakthrough Starshot represents humanity's most serious attempt to design a mission that could travel to another star system at a significant fraction of light speed, possibly up to 20% the speed of light. That's around 60,000 kilometers per second, nearly 200 times faster than any spacecraft ever built. To put that in perspective, at 1/5 the speed of light, a probe could reach Alpha Centauri in about 20 to 25 years, a time frame within the span of a single human generation. It's an audacious vision, but one that's grounded in solid physics and emerging technologies, even if many aspects are still purely theoretical today. The core concept behind Breakthrough Starshot is both elegant and radical. Instead of launching a massive rocket with engines and fuel, the mission proposes sending tiny spacecraft, called starships, attached to ultra-thin reflective sails. These miniature probes, no larger than a computer chip and weighing just a few grams, would be accelerated to incredible speeds not by onboard propulsion, but by powerful ground-based lasers beaming concentrated light from Earth. Here's how it would work. From a massive array of high-power lasers on the ground, collectively forming a 100-gigawatt light beamer, an intense beam of energy would be directed at the sail of each probe. The sail, made from a lightweight, highly reflective material like graphene or metamaterial composites, would catch the photons like a kite in the wind, except the wind here is light itself. Each photon carries momentum, and when reflected, that momentum transfers to the sail, pushing it forward. Over the course of just a few minutes, this beam could accelerate the tiny probe to a significant fraction of light speed. No fuel, no engines. Just light pushing a sail, the ultimate expression of efficiency. This concept leverages the same physics as solar sails, which use natural sunlight for propulsion, but at an exponentially higher power. Where solar sails provide a gentle, gradual push, Starshot's laser propulsion delivers an intense burst of acceleration, achieving interstellar speeds in record time. However, such innovation comes with monumental challenges. For one, generating and focusing a 100-gigawatt laser beam is beyond current engineering capabilities. To put that power in perspective, it's equivalent to the total output of 100 nuclear power plants, concentrated into a single coherent light beam and precisely targeted through Earth's atmosphere onto a sail tens of thousands of kilometers away. The beam would need to remain focused on a sail only a few meters wide for several minutes, without dispersing or damaging the fragile structure. Then there's the issue of sail material. The sail must be extraordinarily lightweight, yet capable of withstanding the immense radiation pressure and heat generated by the laser beam. Traditional materials would vaporize under such conditions. Engineers and physicists are exploring graphene-based nanomaterials, dielectric mirrors, and photonic crystals that could reflect nearly all incoming energy, minimizing absorption and thermal stress. Even if the acceleration problem is solved, navigation and communication pose their own hurdles. At 20% of light speed, even a single grain of dust in interstellar space could destroy the probe. The tiny starship must be able to orient itself, collect scientific data, and transmit that data back to Earth with an antenna smaller than a fingernail. That's like sending a signal from a smartphone across an ocean, except this ocean is 40 trillion kilometers wide. The delay alone would be 4 years each way, even traveling at light speed.
Still, the potential rewards are enormous. A successful Starshot mission could send dozens, even hundreds of these microprobes to Alpha Centauri, increasing the chance that some will survive the journey. Upon arrival, they could take close-up images of Proxima Centauri b, a potentially Earth-like exoplanet orbiting our nearest neighboring star, and beam them back to Earth, giving humanity its first real glimpse of another habitable world. And Breakthrough Starshot isn't the only interstellar concept under development. NASA has also explored ideas for fusion-powered starships under its Innovative Advanced Concepts, or NIAC, program. One such design, the Bussard ramjet, theorized in the 1960s, imagined a spacecraft that could scoop hydrogen atoms from interstellar space, compress them, and use them as fusion fuel, effectively refueling itself along the way. While purely theoretical and far beyond our current technological capacity, the Bussard concept remains one of the most visionary ideas for sustained interstellar flight. Another approach under discussion is antimatter propulsion, where matter and antimatter annihilate upon contact, releasing vast amounts of energy. This could, in theory, propel a spacecraft at speeds approaching 50% of light speed. However, creating and storing antimatter safely, even in microscopic quantities, remains one of physics' most daunting challenges. The world's particle accelerators can only produce nanograms of antimatter at enormous cost, and no containment system yet exists that can safely store enough for propulsion. More modestly, fusion-based systems like the aforementioned Direct Fusion Drive or Project Daedalus, a 1970s British Interplanetary Society concept, aim to reach speeds of 5 to 10% of light speed, sufficient to reach nearby stars within a century. While this doesn't sound fast by cosmic standards, it represents a colossal leap forward compared to our current chemical or even nuclear propulsion capabilities. The idea of interstellar travel also forces humanity to confront a profound philosophical reality. Even if we can't go ourselves, our machines might. A fleet of robotic explorers traveling between the stars, powered by light, guided by artificial intelligence, and transmitting their findings across the cosmic void, would mark a new era in our evolution. It would mean that for the first time, Earth has reached beyond the sun's influence, planting technological seeds of civilization among the stars. In many ways, Breakthrough Starshot represents the first practical blueprint for achieving that dream. It doesn't rely on breaking physics or invoking exotic phenomena like warp drives or wormholes. Instead, it uses the laws of physics we already understand, pushed to their absolute extremes. It's the scientific equivalent of shooting an arrow across the ocean and hoping it lands on an island we can't yet see, but knowing that, for the first time, we might actually hit the mark. Whether Starshot or similar projects will succeed remains uncertain. The technological challenges are immense, and the timeline stretches decades into the future. But the significance of even attempting such a mission cannot be overstated. It symbolizes the transition of humanity from a planetary species to a truly interstellar civilization in thought and intention, even if not yet in reality. And while the stars remain far, the very act of designing missions to reach them forces us to innovate here at home, developing materials, energy systems, and communication technologies that could revolutionize how we explore our own solar system first. Every breakthrough in interstellar research trickles down to faster, safer, and more efficient space travel closer to home. As we stand at this threshold, it becomes clear that interstellar ambitions aren't just about reaching other stars. They're about expanding the boundaries of what humanity dares to imagine. We may not yet be ready to step among the stars, but for the first time, we're building the tools that could one day make it possible. As we've explored the astonishing feats of spacecraft and the even grander visions for the future, it's important to pause and ground ourselves in reality, to reflect on what's truly possible right now with the technology humanity currently possesses. The dream of zipping across the solar system or reaching the stars at a fraction of light speed remains just that, a dream. Our progress is remarkable, but it's also clear that the cosmos operates on scales of speed and distance that make even our fastest machines seem painfully slow. Understanding these practical limits gives perspective not only on how far we've come, but also on how far we still have to go before interstellar travel becomes more than theory.
Right now, the fastest human-made object ever created is still NASA's Parker Solar Probe, which reached about 700,000 kilometers per hour, around 430,000 miles per hour, as it skimmed past the sun. To put that in context, that's fast enough to travel from New York to Tokyo in less than a minute. And yet, even at that incredible velocity, Parker would take over 6,500 years to reach the nearest star. That gap between what's achievable and what's required for interstellar exploration is staggering, a humbling reminder that the universe is vast beyond comprehension. For crewed spacecraft, the limitations are even more stringent. The Apollo missions of the 1960s and 70s still hold the record for the fastest humans have ever traveled at roughly 39,000 kilometers per hour during their return from the moon. Modern spacecraft, such as SpaceX's Crew Dragon or NASA's planned Orion capsule, operate at much lower speeds, typically under 30,000 kilometers per hour in orbit. Even with the most powerful rockets currently in development, such as the Space Launch System, SLS, or Starship, crewed missions to Mars are expected to take several months, not days or weeks. That's because speed is not the only factor. Safety, life support, and fuel efficiency matter just as much, often forcing trade-offs that limit maximum velocity. When it comes to robotic missions, we can afford to take far greater risks. Probes like New Horizons, which flew past Pluto in 2015, and Voyager 1, now traveling through interstellar space, represent the upper limit of what we can achieve using traditional chemical rockets combined with gravity assists. New Horizons launched from Earth at about 58,000 kilometers per hour, while Voyager 1's journey through the outer solar system brought it to roughly 61,000 kilometers per hour. These speeds are impressive, tens of times faster than a bullet, but on the cosmic scale, they're still crawling. Voyager 1, for all its speed, has taken nearly half a century just to cross the boundary where the sun's influence ends, and it will take tens of thousands more years to reach even the closest stars. One of the biggest bottlenecks in reaching higher velocities is the energy cost of acceleration. The faster a spacecraft travels, the more energy it takes to keep increasing its speed, and that energy grows exponentially as you approach the speed of light. Even if we had engines efficient enough to sustain continuous thrust, the amount of fuel or energy required would be staggering. For chemical rockets, the fuel-to-payload ratio is already extreme. Most of a rocket's mass at launch is propellant, not cargo. Nuclear or ion propulsion systems improve efficiency, but they still operate within the same basic physical constraints. Then there's the issue of environmental hazards at high velocity. In interplanetary space, dust particles and micrometeoroids are relatively harmless at normal speeds, but at a fraction of light speed, even a tiny grain of sand becomes a destructive projectile. The kinetic energy from a collision increases with the square of the velocity, meaning that traveling just a little bit faster can exponentially amplify the risk of catastrophic damage. For robotic missions, we can accept that risk. For human missions, it's unacceptable. The need to protect crews from both radiation and high-speed impacts sets a hard limit on how fast we can safely travel using current materials and shielding technologies. From a purely practical standpoint, our realistic ceiling for robotic spacecraft today lies somewhere between 60,000 and 700,000 kilometers per hour, depending on the mission profile and propulsion method. For crewed missions, the practical upper bound is around 40,000 kilometers per hour, achievable only during translunar or transplanetary trajectories. Anything beyond that would require new propulsion physics or revolutionary breakthroughs in material science, power generation, and life support. The next big step will likely come not from faster rockets, but from smarter trajectories and more efficient propulsion systems. Hybrid technologies, combining chemical propulsion for launch and ion or nuclear propulsion for sustained travel, could cut trip times to Mars or the outer planets significantly. Realistically, a trip to Mars might one day take 90 days instead of 9 months, while robotic probes could reach Jupiter or Saturn in just a few years rather than decades. These are monumental gains in the context of space exploration, even if they seem small compared to science fiction. And yet, these incremental improvements are crucial. Every increase in speed, every advancement in propulsion represents a step closer to making the solar system more accessible. Faster travel means shorter mission durations, less exposure to radiation, and more flexibility in launch windows, all of which make deep space exploration more feasible.
For example, reducing the time it takes to reach Mars not only protects astronauts, but also simplifies logistics, allowing for more frequent missions and potentially establishing a continuous human presence beyond Earth. But for all our progress, the speed of light remains an unyielding wall. At roughly 300,000 kilometers per second, it's a limit that defines the structure of the universe itself. Einstein's theory of relativity tells us that as an object approaches light speed, its mass effectively becomes infinite, and it would require infinite energy to accelerate further. That's why all the futuristic concepts we've discussed, from fusion drives to laser sails, still operate at fractions of light speed, not anywhere near the actual limit. Even traveling at 1% of light speed, or about 3,000 kilometers per second, would be an unimaginable leap from where we are now and still require extraordinary energy resources.
So while humanity has made tremendous progress in speed, we remain in the early chapters of the story. Our achievements, reaching the moon, exploring the outer planets, touching the sun with a probe, represent the dawn of true spacefaring capability. The dream of interstellar travel may not be realized in this century, but the steps we take today lay the foundation for those who come after us. Every improvement in propulsion, every experiment with new technology brings us a little closer to bridging the impossible distances between stars. For now, our fastest spacecraft continue to drift outward, silent ambassadors of human ingenuity, marking the edge of what we can achieve with today's tools. And while their journey is slow by cosmic standards, it's a testament to our perseverance, proof that even within the limits of physics, humanity is determined to push as far and as fast as it can. As we reach the conclusion of our journey through the story of speed in space, it's worth stepping back and taking a long, thoughtful look at what it all means, not just in terms of numbers or technology, but in terms of perspective. Humanity's progress in exploring the cosmos has been nothing short of astonishing. In just over a century, we've gone from fragile wood and fabric airplanes sputtering a few meters above the ground to spacecraft that streak through the solar system at hundreds of thousands of kilometers per hour. We've broken free from Earth's gravity, walked on the moon, and sent machines to the farthest edges of the sun's influence. Yet, even with all that progress, the truth remains humbling. The universe is vast beyond imagination, and our speed, as impressive as it may seem, is still infinitesimal compared to the scale of the cosmos. The numbers tell the story clearly. The Parker Solar Probe, our fastest human-made creation, flies through space at nearly 700,000 kilometers per hour, while light races at nearly 1.08 billion kilometers per hour. That means Parker is traveling at less than 0.1% of light speed. Even Voyager 1, the most distant spacecraft we've ever launched, which has been traveling for nearly half a century, would need over 70,000 years to reach the nearest star. These comparisons illustrate not only the staggering distance between planets and stars, but also the enormous technological and energetic barriers that still stand between us and the dream of interstellar travel. And yet this contrast doesn't make our accomplishments smaller, it makes them more extraordinary. Because in a universe that seems designed to keep us grounded, we've already managed to rise. Every rocket launch, every gravity assist, every silent probe sailing through the dark is a statement of defiance against cosmic odds. It says that even though we are small and fragile, we are endlessly curious and capable of transcending our limits through ingenuity and persistence. When we reflect on how far we've come, it's easy to forget how recently all of this began. Barely 100 years ago, human flight itself was in its infancy. The first orbital spacecraft flew in the late 1950s. The first humans ventured beyond low Earth orbit only a decade later. And within that same century, we've reached the moon, explored every major planet, and sent robotic emissaries toward the stars. The speed of our progress in understanding, technology, and ambition is breathtaking in its own right. But the gap that remains, the chasm between where we are and where we wish to go, serves as both a challenge and a compass. The fact that we cannot yet travel anywhere near light speed reminds us that we're still bound by nature's rules, still learning how to harness the forces that govern the universe. The dream of reaching other star systems may take centuries, perhaps millennia to realize,
But every discovery we make brings us closer. The development of ion propulsion, solar sails, and nuclear drives are all stepping stones, pushing us inch by inch toward faster, more efficient means of travel. Still, perhaps the most profound lesson here is not about speed at all. It's about patience. After all, space is not a race to be won, but a frontier to be understood. While the distance between us and the stars is almost unfathomable, the journey itself, the act of trying, of exploring, of daring to go further, is what defines us as a species. We may not reach Alpha Centauri anytime soon, but we're already living in the era of interplanetary exploration. We're preparing for human missions to Mars, sending probes to asteroids, and studying the outer planets with precision instruments that were once unimaginable. Each mission, each leap in technology, is a quiet promise to the future that humanity will not remain confined to one world forever. The barriers we face today, whether technological, financial, or physical, are temporary. Sooner or later, our understanding of physics, energy, and propulsion will evolve. New forms of travel, new engines, or perhaps entirely new ways of thinking about movement through space will emerge. Just as the steam engine gave rise to the rocket, so too will the rocket give rise to something greater. And perhaps that's the true beauty of this story, that in chasing speed, we are really chasing understanding. Every time we push the limits of how fast we can go, we also deepen our grasp of how the universe works. In studying motion, gravity, and energy, we uncovered the building blocks of existence itself. The quest for speed is, in a sense, a quest for meaning, for our place in a universe that seems both infinite and indifferent. So how fast can we travel in space right now? The honest answer is not nearly fast enough to reach the stars. But that's okay, because for the first time in history, we can leave our planet. We can travel to other worlds, touch the edge of the sun's fury, and send our voices, in the form of data and signals, across billions of kilometers of empty space. Our reach already extends far beyond our homeworld, and it grows every year. When future generations look back on this era, they won't see our limits. They'll see our beginnings. They'll see the Parker Solar Probe, the Voyagers, the Mars rovers, and the countless missions yet to come as the first sparks of an awakening species learning to navigate the stars. So while we may still move at a fraction of light speed, in the grander sense, humanity is accelerating faster than ever, in knowledge, in capability, and in imagination. The universe may be vast, but we are already reaching out to meet it, one mission, one discovery, and one heartbeat at a time. Because even if the stars are distant, the journey towards them has already begun.
This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.